we're going to take a look at the pattern we see in the first, second, and third ionization energies for atoms. The first ionization energy is removing a single electron from a neutral atom and converting the atom into a 1+ ion. Second ionization energy is removing a second electron from something that's now 1+, turning that into a 2+ ion. And the third ionization energy is removing a third electron from something that is now a 2+ ion, converting it into a 3+ ion. General trend in this is that the first ionization energy will always be less than the second ionization energy, which is always less than the third ionization energy. This particular pattern is something that's always going to be true. First is less than second, which is less than third ionization energy. In the first ionization, what's occurring is we have a neutral atom in which the number of protons is equal to the number of electrons. We're wanting to remove a single negatively charged electron from that neutral atom. In the second ionization, we now have the circumstance where the number of protons is now greater than the number of electrons by 1. Still, though, what we're trying to do in ionizing is taking another electron and removing it from what is now a +1 charged ion. Moving on to the third ionization, the number of protons is now even greater than the number of electrons. Then we have 2 more protons than electrons present to create a positively 2 charged ion. The third ionization is still removing an electron, but now we're trying to take a negatively charged electron away from something that has a +2 charge on it. The overall effect that we see here is that as we remove one electron, then another electron, then another electron, there's a number of protons in the nucleus is continuing to remain the same. However, the number of electrons in the outer electron cloud is diminishing by 1 with each successive ionization energy. This results in a greater attractive force between the nucleus and the outermost electron, resulting in more energy needed to remove a single electron. And we see the pattern of first ionization energy be less than second ionization energy, which is less than the third ionization energy. We see this pattern in some data for several elements: sodium, magnesium, and aluminum. With sodium, we can see a jump as we go from the first to second ionization energy. Magnesium, we increase first to second, second to third. And in aluminum, there's an increase in required energy from the first to the second, second to third, in this case, third to the fourth ionization energies. Within this trend, though, there's other patterns that emerge. For example, in sodium, we can see a very large jump in energy from the first to second ionization energy, whereas in magnesium, we see a large jump as we go from the second to the third ionization energy. And aluminum, this large jump in energy required doesn't occur until we get to the fourth ionization energy, going from third to fourth. Let's use magnesium as an example to explain why we see these dramatic jumps in ionization energy at different locations with atoms. In magnesium, our nucleus has a charge of +12. And we have the number of protons in a magnesium atom is equal to the number of electrons. So we have a neutral structure. When we're going to ionize magnesium, we're going to remove a single electron from the outermost energy level, which in this case for magnesium is at energy level 3. Now energy level 3, the distance from the nucleus, which has a +12 charge, the outermost electron, the distance that we see between the outermost electron and the positively charged nucleus has an impact on the force of attraction according to Coulomb's law. The distance here would be what we're measuring between the nucleus and the outermost electrons, and we have the effective nuclear charge. This generates a force of attraction between the nucleus and the outermost electrons, which influences how much energy is required to remove the electron from the atom. We see for magnesium, the first ionization energy is going to require 738 units of energy. Once the single electron's been removed, we've created an Mg1+ ion. And this would now be the arrangement of electrons that we have. One electron's been removed from the 3s sublevel. And what occurs is that the distance between the nucleus and the outermost electron shrinks slightly because we now have more protons than we have electrons. So the overall attraction of the protons and the electrons is slightly stronger, which pulls all the energy levels a little bit closer down towards the nucleus. Again, because the number of protons is greater than the number of electrons, what this does is create so that we now have a slightly smaller distance between the nucleus and the outermost electron, or 3s electron that remains. A smaller distance means the attractive force is going to be slightly greater. We see that by an increase in energy, as now we go to 1450 units of energy are now required to remove the second electron from the Mg1 plus ion for the second ionization energy. When we now look at the atomic arrangement for an Mg2 plus ion, we can see the number of protons is greater than the number of electrons. Well, another thing is that the N equals 3 energy level is now gone. It's missing from the structure because when we extracted the electron from the 1 plus to turn it into a 2 plus ion, the N equals 3 energy level is now has no electrons in it, is no longer part of the atomic structure. Because the outermost energy level 3, is now missing from the atomic structure as we go to an Mg2 plus ion, the distance that we see between the nucleus and the outermost electrons is now much, much less, because the outer electrons are only at energy level 2 rather than 3. This much smaller distance, when we take a look at Coulomb's law, dividing by d squared, since that's gotten smaller, the force required to remove an electron now becomes much, much greater, because the force of attraction is greater between the nucleus and the outermost electrons, which is why we now see the jump in ionization energy for magnesium. When we're going from a +2 to +3 ion, we jump from 1450 units of energy all the way up to 7,730 units of energy, largely because we're extracting an electron now from energy level 2 rather than energy level 3, and that's closer to the nucleus, so the attractive force between the nucleus and the outer electrons has gotten greater, requiring a greater amount of energy to now remove an electron. Let's recap and revisit what we just talked about with magnesium to explain why we see this jump in ionization energy, but this time we use sodium. And sodium for the first ionization energy, we see 496 units of energy. And then a dramatic jump where it's almost 10 times as much to extract the second electron for the second ionization energy in sodium. For the first ionization energy, we see that the number of protons is equal to the number of electrons in the nucleus. The outermost electron, which will be getting extracted when we ionize, is at energy level 3. And it's a distance away from the nucleus, and that distance helps us using Coulomb's law to establish the overall force of attraction between the nucleus and that outermost electron. The distance that we have here, we're using Coulomb's law. That helps us figure force of attraction, and that force of attraction influences how much energy is needed to take that electron and remove it from the atom and turn this into a 1 plus ion for the first ionization energy. Now, the electronic structure of a sodium 1 plus ion would look like this, where we now see that energy level 3 is now completely missing, because when we removed this 3s electron to create the 1 plus ion, there's no longer electrons remaining in energy level 3, so that energy level is no longer part of the atomic structure. The distance that we now see between the outermost electrons and the nucleus is much, much smaller. Now, because there's more protons than electrons, one thing that occurs is all the energy levels get pulled a little bit closer to the nucleus due to electrostatic attraction, and we have energy level 3 missing. The overall effect is that our distance between the nucleus and the outermost electrons, when we have a sodium 1 plus, this is now much smaller than it was previously. So to go from sodium 1 plus all the way up to sodium 2 plus for the second ionization energy, you see this big jump in energy. It's because we're now trying to extract a single electron from energy level 2. Energy level 2 is closer to the nucleus, so we have a much smaller distance between the nucleus and the outermost electrons. That smaller distance tells us that according to Coulomb's law, the force of attraction between the nucleus and outermost electrons will increase, and we see a significant change in the amount of energy required to remove this electron and go from a 1+ to 2+ sodium ion. So we can explain this pattern that we see of dramatic jumps here in sodium from first to second ionization energy, magnesium second to third ionization energy, and aluminum in the third to fourth ionization energy. This dramatic jump we see in energy required to remove an electron is an indication that we're moving the electron from a now lower energy level that is closer to the nucleus. Because we're at a lower energy level and closer to the nucleus, the attractive force between the nucleus and the outermost electrons becomes stronger, and that increase in attractive force is reflected by a greater quantity of energy that we see that's required to remove that outermost electron.